Okay, so a couple of years ago, I gave a talk at World Meteorology Day here on the use of infrared thermometers for trying to detect fever related to COVID. And my conclusion from that was that they're a waste of time. So now I'm going to show you that maybe they're not such a waste of time if you try and measure food products in the food industry. And so this talk is really about how the infrared thermometers work and what sort of accuracies we can get out of them when we apply them to the food industry. So they are used increasingly in supermarkets and food processing industries, as well as also lots and lots of other applications, as you're probably aware of. But so why would we want to use infrared thermometry in the first place? Because there's plenty of good contact probes that we can use that measure temperature reasonably accurately. So there's a number of advantages. The first is that obviously they're non-contact, so you're not sticking a probe inside a product and possibly contaminating it. So normal contact probes take a long time to respond. Once you've inserted it into the object, it might take a couple of minutes before you can get a reliable reading. And often in the food industry, particularly in supermarkets, we want to do lots of measurements over a short time. And so the response time of most infrared thermometers is usually less than a second or maybe a couple of seconds. So we can do lots of measurements pretty quickly. And we can also measure at a distance because they measure radiation that's emitted by objects. We can do that over quite a large distance. Pretty much in principle, any distance, we can measure the temperature of the sun if we want to. But there are some problems. And the problems are related to reflection, what I call reflection errors, which is the radiation from the surroundings reflecting off the object that we're trying to measure. And there's things related to the emissivity of the object we're trying to measure, and I'll just describe what that is. And there's also, because we're measuring, in the food industry, we're measuring sort of temperatures around room temperature, or maybe 100 degrees or so. The temperature of the detector itself has an influence on the results. So in order to understand how these things work, we need to understand a little bit about electromagnetic radiation and the electromagnetic spectrum. So it turns out that every object above absolute zero, which is every object, emits electromagnetic radiation in the form of either heat or light. And Annette has just mentioned that William Herschel discovered heat in the infrared. So we're familiar with things like a pot-belly stove. If you put your hands above a pot-belly stove, you can feel the heat being radiated by the stove. If you look at an electric heater, you can see the radiation as well as feeling the heat. A desk lamp turns out to be pretty bright and you can't really look at it very comfortably. And of course, the sun is emitting massive amounts of radiation, which keeps our planet going. And so it turns out that we normally associate radiation with hot objects and often dangerous objects, but it turns out that everything radiates. So even at room temperature, things are radiating about 500 watts per square meter. So you think of a human body, I don't know what the surface area of a human body is, maybe a half a meter squared or so. So we're radiating a few hundred watts ourselves. So every body in this room is radiating several hundred watts. So we're all pretty good heaters. And if we just think about the visible radiation that we see, so as objects get hotter and hotter, the radiation that we see that's emitted changes color. So at 500 degrees, things become just visible. And then as the temperature increases, the colors change through sort of reds and oranges and up to white and sort of dazzling white. And that's related to the temperature. And so in principle, we could use the color to determine temperature. So if we can measure the color of something, we know what temperature it is. And apparently people in the steel industry can estimate temperature to maybe plus or minus 50 degrees just on the basis of color. But it's not a particularly accurate way of doing it. So that's not how radiation thermometers work. And so there's two things that are happening: is the color is changing, but also the brightness is changing. So it's much easier to determine temperature from the brightness of an object than from its color. So the electromagnetic spectrum, you're probably all aware of this, extends over all wavelengths. So if you go to the short wavelength end, this is the high energy, sort of dangerous end. And so we've got things like gamma rays, X-rays, and then as we go to longer wavelengths, we get into ultraviolet. And there's a very narrow part of the spectrum, which is called the visible part of the spectrum. That's the part of the spectrum that our eyes are sensitive to. And you can see on that scale, it's extremely narrow compared to the whole spectrum. As we go beyond the visible into the infrared, we get the infrared and we get microwaves and we get radio waves. And so the shaded region on that graph there is what we call thermal radiation. That's an arbitrary boundary really, but most radiation thermometry is done within that zone between about 0.5 microns and about 20 microns. And so way back in 1900, Max Planck discovered an equation for how radiation is emitted from objects at various temperatures. And it turns out, if you looking at those figures there, different temperatures have different spectrums of radiation. And at 300 Kelvin, which is around room temperature, all of that radiation is in the infrared part of the spectrum, which we don't see. As you go to higher temperatures, the peak of the radiation shifts to shorter wavelengths and the intensity gets much higher. And at about sort of 500 degrees C, which is about 800 Kelvin, those curves start to overlap with the visible part of the spectrum. And that's when we start to see objects glowing when the radiation overlaps that part of the spectrum. So basically to design a radiation thermometer, we pick a particular wavelength and we measure the intensity of the radiation at that wavelength, and we can determine from these curves, we can determine what the temperature is. And you'll see as you go to higher temperatures, the peak moves to shorter wavelengths. So different temperature ranges require thermometers working at different wavelengths. So for applications in the food industry, where we're talking about room temperature or maybe 100 degrees or so, the wavelength that's used is around 10 microns. So it's sort of in the middle of that 300 Kelvin curve. And so they're the types of thermometers I'll be talking about for the rest of the talk. So this is called a black body curve. A black body is an ideal object. It's not a real object. It's a perfect emitter of radiation. But real objects radiate less than a black body. You can't radiate more than a perfect emitter. And so we describe how much radiation an object radiates by a term called emissivity. And it's a number between 0 and 1. And it's just equal to the radiance of the object. Radiance is essentially brightness. Radiance of the object divided by the radiance that a black body would have at the same temperature. And so if we look at two extremes, on the left, we have a real black body, or an ideal black body, which has an emissivity of 1. Because if you take the ratio of a black body radiance to a black body radiance, you have to get 1. And on the right-hand side, we have a perfect reflector, where the emissivity is 0. And so it turns out for all opaque objects, if you take the sum of the emissivity and the reflectivity, you always get 1. And so a real object will be somewhere between these two extremes. It might have an emissivity of say 0.85, in which case it'll have a reflectivity of 0.15. And so in practice, all real objects both emit and reflect radiation. But it's the emitted part that tells us the temperature. So we need to somehow deal with this reflected radiation. We also need to deal with the fact that we might not know the emissivity of the object. So let's look at the emissivity of some typical non-metal objects at 10 microns. And so if you look at these numbers, they're all relatively high, or relatively close to 1. There's nothing there close to 0. So most food products themselves have emissivity somewhere between 0.85 and 1. Glass, now this goes back to the Menti question. Glass has an emissivity of 0.85, which this is at 10 microns. In the visible, glass is transparent. We can see through glass. It doesn't have a very high emissivity. It doesn't have a very high reflectivity. But in the infrared, the glass is essentially black, very black. So when you aim your radiation thermometer at a mirror, you're measuring the temperature of the glass because the glass is black at 10 microns. There is a little bit of reflectance, and so you will see a little bit of your body temperature. Well, actually, you probably see the end of the thermometer temperature because it's what we call a specular reflector. If the reflector was on the front of the mirror, a front surface reflector instead of a back surface reflector, you would measure your own temperature. So I think we had a range of answers on that Menti question, and you can probably consider them all being right to some extent, but the most right one is it would measure the temperature of the mirror. So in the food industry, a lot of the food products are obviously packaged, and we want to measure the temperature of the packaging, measure the temperature of the packaging to infer the temperature of the product inside. And if you look at, for example, paper or cardboard or plastics, they all have quite high emissivity, somewhere around 0.95 generally. And it turns out it's much easier to measure the temperature of a high emissivity object than a low emissivity object. So this is quite fortunate for the food industry. If you look at metals, it's a different story. Shiny metals have very low emissivities, sort of up to maybe 0.15 if it's very polished material. So if you've got a food product that's wrapped in an aluminium foil, or you've got aluminized plastic packaging, like on some chippy packages, for example, not that you probably want to measure the temperature of a chippy package, but it would be highly reflective, and so you would have problems measuring those products. Okay, so I'm just going to talk a little bit about a practical black body, because I said those black body curves are for idealized objects called black bodies, which don't exist in practice. But when we calibrate a radiation thermometer, we want to make it read correctly when it's measuring a black body. So we can make what's called a black body cavity, and we can make it arbitrarily close to a real black body. And so the idea here is that every point on the inside of that cavity is both emitting radiation and reflecting radiation from other parts of the cavity. And so using this property that emissivity plus reflectivity equals 1, the effective emissivity due to all those emissions and reflections inside the cavity, because it's all at the same temperature, means that the effective emissivity of the cavity is very close to 1. Now I say it's close to 1, it's not exactly 1, because there's some rays that escape through the aperture on the front of the cavity. And of course we need an aperture on the front because we're using this as a calibration source. We need to peer inside the cavity in order to measure a signal. And so if there was no opening, we wouldn't be able to look inside. So if there was no opening, it would be a perfect black body, but the opening means it's slightly less than a black body, and we can calculate. There's an equation that tells us how to calculate what the effective emissivity based on the length, L, the radius of the opening, and the emissivity of the material that the cavity is made from. And so if we put some typical numbers in, say we have a material that's an emissivity of 0.9, which is pretty easy to find, and opening of 25 millimeters length, 200 millimeters, the effective emissivity is 0.9948. So it's very close to being a real black body. And these are the things that we use to calibrate infrared thermometers. So what does a thermometer actually measure? So if we're inside a room and we want to measure the temperature of a product, then there's going to be some emitted radiation. So the product is at some true temperature and it has an emissivity. Of course, the radiation coming from the objects is going to be emitted in all directions, but I've just drawn the ray that goes towards the thermometer there. And so the signal that the thermometer measures is equal to the emissivity times the signal that's emitted from the object itself. Because remember, the object itself is not a black body, so it doesn't radiate as much as a black body. It radiates a little bit less by this factor of the emissivity. So this is the first term. It depends on this is the thing that we want to measure, the true temperature of the target, but also there's radiation from the walls and from everywhere else that reflects off the target. So that's the second term, and that term obviously depends on the temperature of the surroundings and the reflectivity of the object we're trying to measure, which is equal to 1 minus the emissivity. And again, the surroundings are going to be emitting in all directions. So I've just picked one ray to draw there, but in reality, there's hundreds and thousands and millions of them. And then there's a third term. So these two components are the amount of radiation that's entering the thermometer. And then there's another term that's actually emitted from the thermometer, because the thermometer itself is relatively warm. It's probably going to be at room temperature. So it's going to be emitting some radiation. And so there's a minus sign on that term. And so we have 3 terms, and somehow from these 3 terms, we need to unravel what the true target temperature is. So if we look at the food industry, if you look at some of the health regulations on storage temperatures for food, so meat products have to be stored between 4 and 7 degrees, fish below 4, shellfish 10 to 15, and frozen products maybe down to -35, depending on what they are. But when we do measurements in the food industry, the surroundings are usually higher or at a similar temperature of the product that we're trying to measure. So that means we have these reflection errors that we have to try and cope with. The emissivity might vary from product to product. Well, as I showed you before, most of the emissivities are around maybe 0.9 or 0.95, but in some cases they might be quite low if there's any metallized surfaces. And so in this industry, we need to try and eliminate both of the errors, these errors due to reflections and due to emissivity, in order to get readings on the thermometer that are going to satisfy those required tolerances. And in some industries, it's actually practical to apply corrections, but in a supermarket or in a storage facility, the operators aren't going to be going around with a computer and typing numbers in and calculating corrections. So we want the thermometer itself to indicate the correct temperature when we do these measurements. And so the question is, how can we do that? Okay, because the signal measured by the thermometer depends on all these different things. It depends on the true temperature of the target, temperature of the surroundings, the temperature of the detector, the emissivity of the target. So what do we do? So most of the thermometers that all of them will have what's called an instrumental emissivity setting. So it's a dial on the device or digital input where you can usually set it between 0 and 1. And I call that the instrumental emissivity setting. And the aim of that is that the user enters the value that is exactly the same as the emissivity of the things the person is trying to measure. And so the thermometer is informed of the emissivity of the target by the user entering that number. And then most manufacturers will then assume that the temperature of the surroundings is equal to the temperature of the detector, which is inside the device. And that temperature can be measured internally with like a thermistor. And it's sort of a reasonable assumption in a lot of cases. If you've got a thermometer that's been sitting in the room for a while, it's going to come to the temperature of the surroundings. So it's a good assumption to make. But as you'll see later, sometimes it's not a good assumption. So once that happens, then the thermometer has some algorithm which processes those numbers and comes up with a reading. Now, if you don't like mathematics or equations, look away now. I'm just going to show you a few. That's the equation I had on the slide 2 slides ago. But here, S brackets T is essentially the calibration curve for the thermometer. That's how the signal on the thermometer is related to temperature if it was measuring a black body cavity, which is what we do when we calibrate. So that's the equation we started with. And this is what the thermometer does with that signal. It takes the measured signal, so it's just usually going to be some sort of voltage. It divides it by the instrumental emissivity that the user has input, and then it measures the detector temperature and adds a component that corresponds to the signal at that detector temperature. And the result of that is this awful equation. But if you look at this carefully, and I'm just going to use the laser pointer so people online won't be able to see it. So there's 3 terms here. So the first term, this is the signal at the true temperature. So if there were no other terms here, then the true temperature or the measured temperature would be equal to the true temperature. That's what we want. These other 2 terms are all of this and all of this are what we call error terms. And so you can see that if we enter the emissivity correctly, that means that the instrumental emissivity is the same as the emissivity of the target. This second term here will be 0. That will be 0 there. And if the temperature of the surroundings is the same as the temperature of the detector, then that first error term will also be 0. So if those 2 conditions hold, and that's the idea that the manufacturers have when they use this algorithm here, if that condition holds, then the true temperature will be correctly displayed on the instrument. If you look carefully at this thing, there's actually another condition where there's 0 error. If we made the instrumental emissivity equal to 1, this first term would be 0. And if the true temperature was the same as the temperature of the surroundings, then the second term would be 0. And in that case, you've got an object that's surrounded by other things of the same temperature. And if you set the instrumental emissivity to 1, so it looks like we've got a black body, the object and its surroundings behave like a black body. And we know that a black body has an emissivity of 1, which is why we set the emissivity to 1 in that case. So I've called these two methods the detector compensation method. That's when the detector is the same as the surroundings, and the black body approximation method. So let's look at these two methods. So the detector compensation method assumes that the surroundings are the same temperature as the detector, and the user inputs the emissivity. And so, as I said before, for most packaging materials in the food industry, the emissivity is 0.95. So that's the value that you would enter. And in fact, there are lots of instruments on the market that don't have an adjustable emissivity setting, but they have a fixed value at 0.95. And that's the reason that it's fixed at 0.95 is because of this. A lot of sort of organic materials, plastics, food, wood, food, etc., has emissivity of 0.95. And so if the temperature of the surroundings is not exactly the same as the detector temperature, we get a residual error. We don't get the true value, but the error is given by that equation. So, for example, if we did have an emissivity of 0.95, that 1 minus the emissivity divided by the emissivity turns out to be 0.09053. And so even if there was a 10-degree error between the surroundings and the detector temperature, that would only be about a ½ degree error in the reading. And you also get an additional error if you haven't actually set the emissivity correctly, obviously. So is this method useful? It's useful in a room temperature environment where the surroundings are all at normal room temperature. In fact, so the temperature of the detector is the same as the temperature of the surroundings. And this will occur, so if you're cooking on a pot, the reflections coming from the hot surroundings, so the room temperature surroundings, and so you're going to get a reasonable measurement there. And if you're in a supermarket, you can measure on the top of an open fridge or freezer, because as far as the thermometer is concerned, the surroundings are all at room temperature. It's not good for measurements inside a cold store, so walk-in fridges or freezers, because the surroundings are going to be much colder than the temperature of the detector. So it's not, the method is not going to work. And it's not going to be very good for measurements at the bottom of a fridge or freezer, because as far as the target is concerned, it's surrounded by other things at the same temperature as itself. And so the surroundings temperature is not the same as the detector temperature. And it's not very good when there are other hot objects surrounding, like heaters and lamps and things. So that's the first method. The black body approximation method, we assume that the surroundings are the same as the target, and we set the instrumental emissivity to 1. And the error in this case is similar to the other one, but it's just 1 minus the emissivity. There's no divided by the emissivity. And that's multiplied by the difference between the surroundings and the true temperature. So this error is much less than the detector compensation method, especially when you go to low emissivities, because at low emissivities, when you're dividing by the emissivity value, which happened in the previous equation, the error gets much bigger quickly. And in this case, the detector temperature is independent. Sorry, the reading is independent of the detector temperature. And you'll see that from looking at one of those equations I showed you before. And so it's useful for measurements in cool stores and freezers where the surroundings are not the same as the detector temperature, but they're the same as the object that we're trying to measure. And it's also good for measuring between objects at the same temperature. So in any sort of environment, if you've got two objects, say two boxes, packing boxes with a gap between them, if you aim into the gap rather than the surface of the box, that gap, that sort of wedge, looks a bit like a black body cavity. And so we can set the emissivity to 1 and get a good measurement. And again, it's not good for cold objects and hot surroundings or vice versa, or when there are hot objects surrounding the target. So we do some calculations. Let's have a look at what the errors might be. So this is a situation where you're measuring at a normal room temperature, so it's at 20 degrees. The detector is also at 20 degrees. We've set the emissivity to 0.95. And these are the errors that you get measuring an object with a range of different emissivities. So you can see over that whole range, minus 20 to 20, the errors are pretty much within 1 degree. If you look at the black body approximation method in this situation, then it's only good sort of just below 0 a little bit, maybe within 10 degrees. Well, sorry, maybe within 10 degrees or so of black body conditions where everything's at the same temperature. So when things are very cold, then it's not working. If we go to the inside a walk-in freezer where the surroundings are at -20, this time the detector compensation method doesn't work particularly well because the detector and the surroundings are at quite different temperatures now. And the black body method is much better in that case. So to summarize all that, with a judicious choice of which method you use to do the measurements, you can use infrared thermometers to get reliable temperature measurements. As I say, use the detector compensation method. So you've got to think about what the situation you've got. Is the surroundings the same as the detector temperature? You don't actually know what the detector temperature is, but it's going to be close to sort of normal room temperature. But in this case, we need to know the emissivity. With the black body approximation method, we don't need to know the emissivity, but we need to ensure that the surroundings are at the same temperature as the target. So that's what I was talking about before, looking between two boxes. You get the interreflections between those two boxes, so that wedge looks like a black body, so you set the emissivity to 1 and you can get a reasonable measurement. Whereas if you're using the detector compensation method, you need to know what the emissivity is. So the black body method works independent of the emissivity of the surface in that case. And as I said before, low emissivity materials are prone to much larger errors. And they grow even faster if you're using the detector compensation method. And so usually in that case, you either have to find a different method, or if you can somehow create a black body. So even if the gap between those two boxes on that picture were quite reflective at a very low emissivity, you'd still actually get a reasonable measurement using that technique.